Greetings, intermediate algebra students. It's time for your first online lesson outside of class anyway. We're actually going to cover a couple different chapters in our book, not chapters, but lessons in our book. So the first one is 1-4 stem and leaf plots, and later on we'll talk about the distributive property. Anyway, one of the things that we will emphasize in this class in an ongoing fashion is the difference between data and statistics. Data, as you can see here, is just the numerical information. If you just saw a list of numbers, that would be considered data. But the statistics part is what we really want to focus on. Statistics is the organizing and interpreting of that data. And as I said, we'll be looking at that over the course of this whole class. Usually a little bit each chapter we might have a particular statistical item that we will look at. So anyway, today our topic is something called the stem and leaf plot. It is a way of organizing and interpreting data. When we come to class tomorrow, we'll be actually working on a stem and leaf plot, practicing on that. Anyway, here's our data right here. You have an example of just a list of numbers. We don't know what they mean or what they're referring to. The stem and leaf plot has two features. The stem, which is kind of the main trunk of this plot, and then the leaves. Typically, if you have a bunch of two-digit numbers like this, the stem would be the tens place. So where the ones, this would be numbers from 10 to 19. The twos would represent 20 to 29, things like that. 3 is numbers in the 30s, 4 is numbers in the 40s. So you can see where the number 32, how that would look. We have a stem of 3 and a leaf of 2. All right, we're just going to practice a bit with some other data here. Let's just say we looked at a couple of Houstons in the United States, Houston, Texas, and Houston, Minnesota. We would like to make something called a back-to-back stem and leaf plot to help us organize this data. Now, what a back-to-back plot is, means we would actually write the stem right in the center here, and then we would have Houston, Texas over here, let's say, and Houston, Minnesota over here. Now, if we look at what our stem should be like, notice that obviously Houston, Texas would be a lot warmer. In fact, they don't have any average temperatures. This is average temperature data, I should mention. Average high temperatures for each month of the year. They don't have any temperatures that are averaging below in the 60s. Minnesota, on the other hand, does have a couple in the 20s, of course, in January and December. So I would take a look at that and I'd try to figure out a nice stem to use. Since Minnesota has numbers in the 20s here, that's what I'm going to start with. So I'm going to say 2, 3, 4, 5, 6, 7, 8, and 9. So remember, in this case, something that's in this 6th row here would be temperatures in the 60s. So I'm just going to go ahead and do this then. You can kind of follow along and watch how I do it, or you could practice doing this yourself by pausing the video and then just seeing if you get it correct later on. So I would just go month by month. So 63 for Houston, I would put a 3 right here. Even though this looks kind of weird, numbers going to the left, this does stand for 63. 63. So I'll just kind of continue on. The next one would be 66, 72, 79, 85. Here's my 90 there for Houston. 92 right there. 93, 88, 81, 72, and 65. Now I'm going to switch colors here and then do the same thing for Houston, Minnesota. Once again, starting with January. So I have 24, 29, 41, 56, 67, 77, 81, 79, 71, 58, 42, and 27. Now you can clearly see as we examine this stem and leaf plot, as you might have guessed, the temperatures for Houston, Texas certainly trend a lot higher, and they are pretty consistent from the 60s to the 90s, whereas you can see Minnesota's data is much more spread out from Houston, Minnesota. We could break this down and analyze it quite a bit more, but right now our main task is to be able to construct a stem and leaf plot. We would call this a back-to-back stem and leaf plot. And it's kind of nice when you're comparing two sets of data that are kind of similar. In this case, the similarity is just the names of the city. All right, so that was kind of fun. Now we're going to go on to the next lesson here, which is something called the distributive property. This is probably about the most famous mathematical property we have, and I'm sure you guys have seen this before. The distributive property involves both multiplication and addition, or multiplication and subtraction. And you'll always have both of those features in any kind of distributive property problem. So the idea here with the distributive property, if I have a number, in this case a, and I'm multiplying it by a sum is when you add b plus c, we say that a actually gets distributed to both b and c. So a lot of times I like to draw little arrows here from a to b and a to c, keeping in mind that a is multiplied by b, a is multiplied by c, a times b, the best thing I can do is say that that's just going to be a times b, because I don't really know what a and b are. And then a times c, I just have to write that as ac. I put a plus sign in the middle because that's what the original problem has, and then I'm done. I can't combine these two things at all. I can't add up letters like that, obviously. All right, let's try a couple examples here. Here's our first one, 3 times 4 plus 2. Wouldn't really need the distributive property for one like this, but let's give it a shot. I'm going to take 3 times 4 and 3 times 2. I'm distributing that 3. 3 times 4 is 12. Put my plus sign here. 3 times 2 is 6. And 12 plus 6 is 18. All right, let's try another one here. This one gets a little bit more like the ones we like because there's a variable here. So again, I'm going to distribute 8 to n and to 2. So 8 times n, we just have to write that as 8n. That's the best we can do there. 8 times 2, though, is 16. Put a little minus sign in between, and we can't put these together. We'll be talking much more about that later on, a little bit later on even in this lesson, or this chapter, about something called like terms. And then the last one we want to look at here then is this one. So again, I'm distributing the 2. So 2 times 4n, I can multiply 2 times 4, so that's 8. The n tags along there. And then 2 times 5 is 10. Again, that's the best I can do. I can't put anything more together. So that's my answer there. That's the distributive property. All right. Now, you might wonder what good the distributive property is. I will tell you that we do use it a lot in mathematics, not only in algebra, but in every other math class that you take. Now, here's a practical use of the distributive property. Most of you might say when you see a little problem like 4 times 998 that would be kind of tough to do without a calculator. And in a sense it would be, but let me show you how easy this would be using the distributive property. So I'm going to write down the 4, that's not going to change. Now another way of writing 998, I think you would agree, is to take 1000 minus 2. That's the same as 998, so I'm just substituting or writing this in place of it. And you might say, well, what good does that do? Well, notice what we can do next. Now I have it set up kind of like the distributive property, and you can probably do these in your head. Can you take 4 times 1000? Well, 4 times 1, of course, is 4, so 4 times 1000 is 4000. And then I distribute the 4 once again to the 2. 4 times 2 is 8. This time I have a subtraction sign in there. So what is 4000 minus 8? Well, that's a little tricky, but you'd have to realize it's almost 4000 just 8 less than that. So that would make my final answer 3,992. All right, last one here, just some terminology here. A term, a number, a variable, a product or quotient of numbers and variables, like terms, exact same variables and exponents, and coefficient is the numerical factor in a term. We're just going to take this example here and see if we can identify these particular properties here. So first of all, the terms, there's actually 4 of them: 10x, negative 3x squared, 4n, and 3x. Those are all terms. I'll separate them with commas, but basically the chunks of this problem. Now the coefficients are what is multiplied by the variables. So we would have 10 for the first one. The second one's a little tricky. It's negative 3, not just plain 3, then 4, and then 3 again. All of those are called coefficients. Now as far as like terms, do we have any of these terms that we could combine together? Remember, they have to be the exact same variables and exponents. Sure enough, we do. Our like terms are going to be this one, 10x, and this one. So if I combine those together, notice I have a 10x, and I can't remember if that was a plus sign or a minus sign. I think it was a plus sign, plus 3x, and 10x plus 3x is indeed 13x. So a key idea here is that we can combine or put together like terms. We'll be doing a lot of this in the rest of this intermediate algebra class. All right, thanks for listening, everybody, and we'll see you guys in class tomorrow. Bye now.